Hello, this is Andy Pilc. It's day 21 of our astronomy unit, and today we are going to get pretty deep in the weeds, talking about some pretty complex space science. In this lesson, we're talking about the relationship between space and time, or like time and matter. So I thought that this would be a appropriate day to talk about one concept that came up in this conversation between Neil deGrasse Tyson and William Shatner, which is why time appears to slow down when you're traveling at very fast speeds. Really quickly, like the inspiration for this kind of came from a book that I stole from my sister a long time ago. Thank you, Jen. Called The Elegant Universe. It was written by Brian Greene, and he talks about these pretty complex concepts that are happening at like the forefront of astrophysics. So in order to talk about why time slows down when objects travel very quickly, Brian Greene introduces this concept of a photon clock. So any clock is based on something that happens in regular intervals. If you think about our clocks, they're based on the sun's apparent motion across the sky, which we've talked about earlier. Every time the Earth rotates one time, it looks like the sun appears to move across our sky, and that's what we base our clocks on. We base our calendars on the Earth's constant and predictable cyclical motion around the sun. Most people's watches use the quartz atom and the amount of times that it vibrates to be able to measure seconds in regular increments. But Brian Greene is going to introduce this concept of a photon clock, meaning the photon in the center is moving up and down between these mirrored panels, and it's traveling at the constant speed of light. Light always travels at the same exact speed. It's very fast. A lot of independent studies have come to the conclusion that it travels at about 680 million miles per hour. So if these mirrors were about 6 inches apart, it would take one photon about a billionth of a second to complete one tick, which is going to count for one round trip. So imagine if we're racing down the block and we're using our photon clock, and this photon is going to move, it's going to make, 55 billion ticks in the time that it takes to finish our race. So because of that, we can conclude that our race took about 55 seconds. But time is relative based on how quickly something is moving or how quickly something appears to move. So if we imagine two of these clocks now, we're going to have one in the forefront that we just talked about. So this one is ticking. The photon is moving up and down, but it's not moving. But relative to this clock, we're going to have a second clock, a second photon clock, and this clock is moving at a constant speed forward. So to us, or rather, if we're on this moving car and we're using our photon clock here, if we were to look down at it, we wouldn't notice anything except for the photon going up and down. However, if you were standing on the side and you were watching this clock move from left to right, and you were watching that photon tick up and down, it wouldn't travel in a straight line anymore. Now, it would travel, in a diagonal line, because if this clock is moving from left to right, then the photon is going to have to travel in kind of this hypotenuse, if you imagine a right triangle here, this longer path. But remember, the speed of light can't change. So because of that, it's going to take a longer time for this photon to complete one tick. When it was stationary, all it had to do was travel 6 inches up, 6 inches down. But now if this is traveling very quickly, it's going to have to travel a greater distance in order to tick one time. Let's just look at one more example. So again, if you are moving at a very fast speed and you're looking down at your watch, all you would see in one tick or one cycle of your watch would be the photon moving up or down. However, if you're watching something move past you, so if we're talking about relative motion, let's see how it changes as that object's speed changes. So this is position 1, position 2, position 3, if the photon clock is moving forward at close to the speed of light, it's going to have to dedicate some of its speed to like a horizontal x component in addition to the up and down y component that we see as we're traveling with the clock. But if we're watching it travel past us, it's going to travel up and then down. If it travels at a faster speed, meaning that photon clock can move from position 2 to position 3, can move from one position to the next quicker, then it's going to have to dedicate more of its speed of light to that x component, and it's going to appear to take a longer time for the clock to tick 1 if we're watching it travel past us, because it has to travel up and down to tick once, but it's also going to dedicate some of that speed of light to a forward motion. Now, if we link this back to what Neil deGrasse Tyson and William Shatner were talking about in the beginning of the lesson, if this photon light is traveling forward at the speed of light, that means that 100% of the speed of that photon beam is going to have to move forward. There's no more speed that it can use to go up and down. That's why they were saying that even though the beginning of the universe is almost 14 billion years ago, if the light from those galaxies has been traveling forward at the speed of light, which it has to, then it will appear, if we were that photon clock, or if we were traveling in some type of space vehicle like it traveled at the speed of light, then it would appear that it would not have any time to go up and down, and therefore it wouldn't tick one time, and therefore time appears to move slower as we travel at very fast speeds. If your brain hurts, so does mine. It's very complicated, but if you're interested in learning more, I can't recommend Brian Greene. This is a pretty old book. He's come out with many more, and he has some pretty cool TED Talks and interviews too. Hope this was interesting and helpful, and I will see you next time.